maybe we can start. Hello, everybody. Today we have a pleasure to listen the talk by Sebastian Mizera. He will tell us about progress on high energy string collisions. 1 hour, please.
All right. Well, thank you, first of all, for the invitation to give this seminar. It's a pleasure to participate in the seminar series. So today I will be talking about string theory. So to me, string theory is exciting because it gives us a rare window into the physics of quantum gravity. So today I will be taking kind of a particle physicist approach to this problem. And I will be studying the following thought experiment. So let's say we take two strings and then we collide them at high energy, just like as if we did it at the particle collider. And then what's going to happen generically is that there's going to be other strings flying out. And you would imagine that by trying to understand the correlations of the outgoing states, their angles, energy, distributions, and so on, we can infer a lot about the physics of what happened at short length scales, somewhere here inside of the collision. So just so that we're on the same page, let me mention a couple of mass scales or length scales that appear in this problem. So first of all, the main scale is the so-called string scale, which you can think of it as a characteristic size of each string. So that's typically denoted by L sub s, but also interchangeably, you can call it as a square root of alpha prime, which is a famous parameter in string theory. And then when we talk about the collisions of strings, we'll be thinking about a very high center of mass energy, square root of s. So by very high, I mean that it's going to be very high compared to the length scale of each string. Okay, so this is going to be the setup. And now let me explain the outline of this talk. So first of all, I will give you some motivation why we want to study these kind of problems. And this will be related to the so-called phase diagram of gravitational scattering. So I will explain that as a motivational part. And this will lead us to studying string perturbation theory. And in fact, I will tell you about some puzzle that has been around for a while about the definition of string perturbation theory in Lorentzian spacetimes. And then ultimately, what I will explain is the resolution of this puzzle, which has to do with the formulation of scattering on Lorentzian worldsheets. And in fact, that last part will result in two separate pieces of new information that we have about these kind of problems. And that will have to do with fixed angle scattering and fixed momentum transfer scattering. So here I kind of flashed some plots. So just a highlight of something that you can look forward to towards the end of the talk, we'll be able to extract some numerical predictions for string scattering at high energies. Okay, so I will start with the first part, which is the motivation. So first of all, let me just kind of answer the simple question of what can be measured asymptotically in a theory of quantum gravity. So let's say you actually had access to these kind of measurements. What can you do in principle? Okay, so once again, we're going to follow the particle physicist approach. And the simplest thing that you can do is you can sense two strings. And then the simplest thing that can come out is two of the same strings. So this would be the elastic amplitude, which is 2 to 2. Another thing which is closer to the picture that I showed you just a couple of slides ago is that we send two strings, but many things fly out. And this would be in principle, including inelastic effects. And if you're wanted to be really close to the type of things that we do in particle physics, you would really think about cross sections in which you really compute the mod square and perhaps integrate out some things that we cannot see in our Gedanken collider X, and then maybe measure inclusively some other particles that fly out. Okay, so this is kind of the menu of the things that you would like to be able to compute. Unfortunately, currently, this is very difficult. So for the purposes of this talk, we'll focus on the simplest version of these measurements, which is the elastic amplitude, in which you have two strings coming in and two strings coming out. Okay, with, of course, the prospect that if we develop enough technology to be able to compute these kind of objects, it will tell us about tools that we can later import to the more complicated types of amplitudes. Okay, so let me first explain the kinematics that we deal with. So here we have the spatial picture. We send in two strings, or two particles in general, with momentum P1 and P2, and the outgoing ones will have momentum P3 and P4. So we typically study this kind of process in momentum space. So everything will be parameterized by two numbers, so-called Mandelstam invariants, S and T. So S is the center of mass energy squared, so P1 plus P2, and that's a time-like quantity, so it's going to be positive. So there's a question already.
Oh, yes, already. Philip, please ask your question. Yes.
Oh, good morning. I'm presuming by strings you mean P1, P2, P3, P4 are 9-dimensional, in which case there will be a lot more than two Mandelstam variables.
There's always only two Mandelstam kinematic invariants, regardless of the spacetime dimension. And that's the number two is limited actually by the number of particles or number of strings, not about the spacetime dimension.
Okay.
Okay, so very good. So the first one was S. The second one was going to be T, which is the momentum transfer squared. So in this case, P2 minus P3. And that's a purely space-like quantity. So people often write it as some space-like vector Q, and then T is minus Q squared. So that's a space-like quantity, it's negative. Okay, so S positive, T negative. So for the most of the talk, I will be working with these Mandelstam invariants. Just for the purpose of the next slide, because that next slide is understood better in the context of impact parameter space, and that's something that I'm sure you've seen in the previous talks as well. This is the one in which you talk about not S and T, but instead of that S and B, where the B is the impact parameter. So roughly speaking, you can think of the impact parameter as the Fourier transform of the momentum transfer. So roughly it's B is 1 over Q. And actually the only thing that matters is not the vector, but its absolute value, which I call B. Okay, so as I mentioned, for the rest of the talk, we'll focus on the momentum space. For the discussion of the phase diagram of gravitational scattering, I'll nevertheless talk about S and B because that's how it's been done traditionally. So this phase diagram is due to the work of kind of enormous body of work that started with the pioneering contributions of Amati, Cefaloni, and Veneziano starting in the 80s, and that's actually something that we're still trying to understand until this day. So if you'd like to learn more about it, I would highly recommend reading this recent review by Di Vecchia, Heisenberg, Russo, and Veneziano on this very topic. For the purpose of this talk, I will just kind of summarize it on one slide, very quick summary. So what you try to understand here is that I discussed these two scales, S, which is the energy, and B. And in fact, let me just make them dimensionless. So B is measured in the string units, and likewise S is going to be measured in the string units. So what you can do is you can study the high energy behavior, but it turns out that the high energy behavior is actually not unique. You have to tell me more precisely how, so both B and S are going to be large, but you have to tell me more precisely at which rates they go to infinity. Okay, so the simplest regime is this one here. So this one is, you can think of it as the impact parameter being very, very large. So this is the regime called Born regime, which is dominated by a single graviton exchange. So this gives us the Newtonian potential. And then what you can do is you can try to think about what happens as you decrease the impact parameter. So more and more new phenomena starts appearing. Okay, so the first thing that starts appearing is the fact that we have the iconal regime. So this is the regime in which you do not have a single graviton exchange, but instead a kind of a whole ladder of gravitons. So I believe this has been discussed or reviewed by Paolo Di Vecchia in a recent seminar in the series. So I'm sure many people are familiar with this already. And then what happens as you keep decreasing the impact parameter even more? then you have tidal effects, and then the generation of gravitational waves. And ultimately, in the kind of regime in which the impact parameter is very, very small, so you can think of it as a head-on collision, you expect that you produce black holes.
Excuse me, can I ask you?
Yes, please ask the question, Igor.
Yes. Is it true that you consider strings like points like objects? What is your in and out states for strings?
Yeah, that's exactly the case in this regime of high energy. You can approximate strings roughly as point particles. Then you can try to add the finite size effects. And in fact, what I'm going to discuss now is that what happens when the string effects become much more important, and they become much more important when the impact parameter goes below the string scale, or like roughly crosses the string scale. So let's say B is of order the string length. And likewise, when the energy is below some cutoff, this cutoff actually turns out to be related to the string coupling. So it's 1 over G string squared. So in this regime here, we deal with a lot of stringy effects. And this is actually the regime in which we can, in principle, try to understand it using perturbation theory. And that has been done since the work of Amatrice and Veneziano, and today I will follow a very similar approach. In fact, what I will do is I will study what happens when you start with a perturbative approach and then you try to take the high energy limit. So in that limit, what you would expect is that we can approach the transition between strings and black holes, okay? So the motivation for studying the high energy limit is trying to understand the dynamics of strings at this kind of high energies from the weak coupling perspective.
Please let me ask a question. Do you have in mind massless states, massless string excitations in this picture?
Yes, that's exactly what I'm going to do in the next slide. So when you here, I will be putting external gluon excitations.
Yeah, because otherwise it's not, you cannot compare just the impact parameter with the string length, but you have an additional scale if you have massive states.
Yeah, that's right. That's
okay.
right. You would imagine that at high energy it doesn't matter, but at the low energies there would be some subtleties. There's also some subtleties with the fact that they would be unstable and so on. But you're absolutely right. What I'm going to do in a couple of slides is specialize to massless external states. Okay, excellent. So in fact, we'll focus on 2 different limits. So that was roughly indicated with the 2 arrows on the previous slide. So first of all, I will be in perturbation theory, which means that the coupling constant G string is going to be fixed and very small. Okay, so if we refer back to this picture, the first limit that you can study is when back in the S and T space, is that S can be large and T can be large. So simultaneously we take them to infinity, but in such a way that the scattering angle, which is the angle between the particles that we scatter, which is equal to this quantity, is fixed. So we take S large, T large, but the ratio of S to T or T to S is going to be fixed, which corresponds to the fixed angle. That's one option that you can study. And another option that we're going to consider is the fixed momentum transfer, which means that we take high energy, but at the same time, momentum transfer is going to be fixed. So this quantity here is going to be fixed. Okay, so this was kind of the motivational part, explaining why we care about these problems. And now I will tell you more about string perturbation theory, how these problems are actually formulated in practice. And then the end of this discussion is that we're going to encounter a small puzzle. Okay, so here, this has been already anticipated by questions. We're going to, for concreteness, focus on gluon scattering in type 1 superstring in 10 space-time dimensions. Okay, so we can actually repeat a lot of this analysis for different types of strings. For example, we can study graviton excitations in type 2. But I wanted to keep things simple for the purposes of this talk, so I will focus only on the gluons. Okay, so one quantity that you can compute is this planar scattering amplitude. So as I mentioned before, it's going to be a function of S and T. And then just like in field theory, in quantum field theory, you can expand perturbatively in terms of Feynman diagrams. In string theory, we expand in terms of different worldsheet topologies. Okay, so this picture denotes scattering of 1 and 2 going into 3 and 4. Where the trajectory spanned by the string is called the worldsheet. And then we can classify the difficulty of the computation of the ordering perturbation theory by the number of holes or the genus of the surface. So at the leading order, we have this contribution here. So this is the analog of the tree computation in quantum field theory. So it's also called the disk diagram. And I'm going to review it in a second, how to compute this contribution. But the bottom line is that everything about this computation has been understood. On the other hand, when we go to subleading orders in perturbation theory, so here G string to the 4th, we have two contributions from genus 1 surfaces. And these are called the annulus and the Mobius strip contributions after the topology of the worldsheet that you can see here. And the bottom line is going to be that there's been some information that has been missing about these contributions, and I will try to address these difficulties in order to actually compute these objects. So what do I mean by compute? Well, in this talk, I will be employing what I call the give me the numbers approach. So this is a very practical, pragmatic approach, which says that by whatever means necessary, I just want to be able to extract numbers out of the numerical predictions out of my string perturbation theory. So if I plug in some value of S and some value of T, positive and negative, I want to get some number out. If I can reliably produce these numbers, it means that I've basically effectively understood everything about these computations, because I can plot them, I can study their low energy or high energy behavior, and so on and so on. So what I will try to convince you of is that this approach can be very successful for the tree at tree level, which is the famous Veneziano amplitude. So it looks like this. So this is the tree contribution to the planar scattering. As I promised, is a function of S and T, and it has this shape. Okay. So this formula has been actually known for a long time. It's in fact been started the whole field of string theory in a sense. Okay, so let me explain this prefactor here, T8. So T8 contains all the contractions of the external momenta P and their polarization vectors epsilons. So in terms looking like this. This is kind of a universal prefactor that is always there. So for the purpose of plotting things, I will just set it to 1. It's understood. Okay, the rest is contained, all these stringy effects are contained in these collections of gamma functions. So they depend on S, T, as well as this parameter alpha prime that I already mentioned before. And the physical interpretation of alpha prime is as the inverse string tension. And here, once again, I can always work in the units. So these are just the units. I can set them to 1. So everything is going to be a function of S and T. So if you wanted to extract the numbers out of this formula, you can easily do it. So here's a plot, just to prove that point. The plot on the horizontal axis has S, the energy. And on the other axis, we plot the planar contribution as a function of S, and then I've plugged the value of T that corresponds to 60-degree scattering angle. Okay, I've also normalized everything by these signs, and that's because the Veneziano amplitude has a number of zeros and poles that correspond to resonances. So this sign is just so that the plot looks nice. Otherwise, you would just see a number of divergences. Okay, and notice that here we are actually on a logarithmic scale. So, and then the numerics follows a straight line, more or less, asymptotically. And this means that at high energy, the amplitude is exponentially suppressed. In fact, it's exponentially suppressed with this S3, which is referred to as the tree-level on-shell action. Okay, very good. So for all intents and purposes, we've understood the high energy behavior of the tree-level contribution. And what I want to explain next is the one-loop correction. So kind of the first quantum correction to the Veneziano amplitude. So as I mentioned before, this it contains the planar annulus and the Mobius strip contributions. In fact, how to write these formulas has been understood for a very long time, and it's by now a textbook material. So this slide is mostly to the experts who would have recognized this formula. Let me just kind of briefly summarize what it's all about. Okay, so this factor here contains a collection of the Jacobi theta functions that depend on z and tau. So the way that you can think of z and tau is that we are going to consider a rectangle with one side has length 1 and the other side has a complex number, which is tau over 2. Okay, so then you identify the opposite edges of the rectangle here and here, and this makes it an annulus. Then we insert punctures on one of the boundaries of this annulus, which corresponds to the external states, Z1, Z2, Z3, and Z4. And in fact, because of the overall rotational invariance, I can fix one of the position, say Z4, to be equal to 1. Okay, so there's a computation in string theory that computes the correlation function of this kind of worksheet, and the result is some ratio of these Jacobi theta functions that looks like this. So the details are not extremely important. What's important is that this ratio depends on the S and T in the following way. And as I mentioned before, this is really an integration. So the integration corresponds to integrating over all geometries of this worksheet. And you have to integrate over the positions of the punctures. So these are the Z's that you integrate in a given ordering. So this is the planar ordering, Z1, Z2, Z3, Z4. And also you have to integrate over the modular parameter, this tau. So you can think of the tau as characterizing the thickness of the annulus. So when tau is very small, then it means that this rectangle is very thin. So the annulus is very thin. This is the kind of Feynman diagram limit. And on the other hand, you can also take tau to be very large. In fact, you have to integrate over all of them, large imaginary, and this corresponds to a very thick annulus. Okay, and likewise, just like we've seen at tree level, the polarization dependence T8 just goes up front, so I can just forget about it. Okay, so all of that.
Hi, I have a question.
Yes, please.
I mean, one would think that the answer should not depend on the overall thickness of the annulus, right?
So what you actually have to do is integrate over all different geometries, and that integral depends on the thickness of the annulus as well.
Okay.
So this is parameterized by the tau. So the final answer does not depend on it because you've integrated over all. It's like a path integral over all geometries.
Okay. All right. All right. Thanks.
Thank you. Excellent. So this was the planar annulus contribution. On top of, so this was the first diagram in here. It turns out you can also analyze the Mobius strip contribution, which is this diagram in here. And in fact, it's given by almost exactly the same formula. The only difference is that you have to evaluate it on a shifted contour. So instead of integrating from 0 to I infinity, you integrate from 1/2 to 1/2 plus I infinity. And the other difference is that this minus sign is replaced with a factor of 32 over n, where n is the refers to the SON gauge group that tells you about the gauge group of the external gluons. Okay, so this is amazing. So basically, we have a formula that you can open a book on quantum field theory. You would see this formula. So the first thing that if you were following the give me the numbers approach, what you would try to do is you would try to just stick it in your favorite software, say Mathematica. And here I've just copied the expression from the previous slide, which is the planar annulus and the Mobius strip contribution. I plugged in some numbers for S and T, and I try to integrate it. And I suspect there could be some people in the audience who had tried doing this in the past, and they would know very well what the result of this computation is. Well, the result is a big divergence. Okay, and it turns out that this is not a numerical issue. This is a kind of a deep issue that has to do with the way that we formulate string perturbation theory on Euclidean surfaces. So the bottom line is that the formulae for string amplitudes that you would see in a book, they cannot be just used directly in practice, in the sense that you cannot just plug it in Mathematica, then click Shift Enter and get the answer. You have to actually do more work. So I wanted to emphasize that it's a physics problem, it's not a numerics problem. And let me just explain precisely where this problem comes from. So on the previous slide, I showed you the integrand that was very complicated, but one aspect of this integrand was that it was real. So you can investigate all the functions that were there, and they were just real. And on top of that, there was an I up front, but also we integrate over the modular parameter tau from 0 to I infinity. Okay, so that tells you we already knew that the answer to this question is infinite because we got the divergence. But in fact, it turns out that because of the reality of the integrand, the answer is not only infinite, it's real. Okay, so it turns out that the reality of the amplitude is actually a very bad sign because it tells you that this computation could not be compatible with unitarity in the target space. So unitarity in space-time. That's because we know the S matrix has to satisfy this unitarity constraint. So unitarity embodies the physical principle of probability conservation. And at the level of the S matrix tells us that the S as dagger is equal to 1.
Oh, excuse me. One more question. Philip, this is your question.
Yes, you'll have to forgive me, but I'm going on a long time memory. What I remember of the Veneziano model was it's a narrow resonance approximation, which doesn't satisfy unitarity to begin with.
So we're actually going to get back to this point in which you have to take into account the widths, the mass shifts, and the widths of the resonances. So I'll explain in a second how this arises. So this would fix the unitarity problem. But in a sense, the problem that I'm mentioning now is much more fundamental. It tells you that the unitarity doesn't break down only in your resonances, it actually breaks down everywhere. Okay, that's a very bad sign. Let me just finish explaining this equation. Here, this basically implies that if the scattering was supposed to be non-trivial, it means that it has to have both real and imaginary parts. Okay, necessarily, in fact, the imaginary parts are associated with particle production. Okay, so that's what was bad about this formula. And let me just give you an analogy with if you did this computation using in quantum field theory. So in quantum field theory, the analogy is directly that what would happen if you try to do loop integration, and then in the denominator you would have just poles associated with propagators going on shell. And if you didn't know about the fact that you're supposed to regulate this with the causal I epsilon prescription, you would get an infinity. In fact, it would be even worse. The infinity would be real. So it's exactly the same problem. And what this means is that, well, in quantum field theory, this is resolved by an Feynman causal I epsilon prescription. So the problem is in string theory is going to be the same, and the resolution is also going to require you to think more about the IAPSM prescription there. So in fact, there's going to be two challenges. So I'm going to distinguish between the conceptual and the computational challenge. So the conceptual challenge is, what is the integration contour? This is the kind of direct analog of the question of what would be the integration contour in the loop for Feynman loop integrals. So equivalently, you can actually phrase this more mathematically as the question about the compactification of the moduli space of Riemann surfaces. And some of you might have heard about compactifications that exist in mathematics, such as the Deligne-Mumford compactifications. But actually, it turns out that they don't work. They don't resolve the very problem that we're trying to address. So what we're trying to address is more or less what is the role of Feynman IAPSM in string theory. And this problem has been actually understood entirely at tree level, although I will not have enough time to explain this resolution. So the one loop, the one that we're studying, is the first interesting case in a sense. And that problem is not new, and in fact has been studied by a number of different people listed here. Okay, so I've learned about it for the first time around from a paper of Witten around 10 years ago, who emphasized the need of resolving this problem. Okay, so this was the conceptual part. Once you've resolved the conceptual part, there's also going to be the computational challenge. So the computational challenge is, okay, let's say we have the contour. How do we actually integrate over it? And here, what happens is that essentially you get something like a sign problem. So it turns out if you actually try to integrate over these contours, you have huge oscillations. So that means that numerically things become very unstable. So even if we could address the first problem, you have to also address the second one. And the way that we're going to do it in practice is by converting a integration problem into an infinite sum. So provided that the infinite sum converges sufficiently fast, then you can actually use it to compute these integrals, and you can plot them, and you can study their high energy behavior, which is in fact what we're going to do in the next part of this talk, which is the longest part. So maybe I should pause here and ask for any questions, that if I can clarify anything.
Yeah, maybe I have a question, Sebastian.
Yeah.
So actually, I don't work in string theory, but I've heard that, for instance, some people working in string field theory,
yeah,
they usually say that the framework of perpetual string field theory can be more useful for this type of loop computations, right? And also there was some paper by Ashok Sen and other people where actually they try also to worry about what kind of contour deformation have to implement in that case.
Yeah,
and in that case, it's some kind of like non-local QFT language, which is more easier for me to understand.
Yeah.
And so my question is string field theory able to solve these kind of problems that you are mentioning here?
So yeah, that's an excellent question. So the string field theory formulates the problem in a different way. So you can think of it more, well, the way that you mentioned, as a kind of Feynman diagrams with non-local vertices. And there is still a challenge of how to define the integration contour that has been addressed by Ashok Sen and collaborators. If you ask about so I believe that this kind of resolves the conceptual challenge within that framework, but there is still the computational challenge. And in fact, I would be very excited if that framework could be also used for making explicit computations and in principle reproducing the plots that I will be talking about next.
Okay.
But absolutely, this is a kind of an alternative approach.
Mm-hmm. Okay, I see. Thanks.
Okay, so before diving into all the details, let me kind of play a small game and ask: could we have predicted how this one loop amplitude is supposed to look like without doing any computations? Or let's just collect what is known about it in the literature and try to put it all on a plot. Okay, so first of all, we have the annulus and the Mobius strip contributions. So they can be cut into two parts by a unitarity cut. So when you cut, just like we do in particle physics, okay? So when you cut a diagram into two parts, there's a number of states that can go, there's some state with mass m1 and some state with mass m2 that go through the cut. Okay, so there's going to be mass 1 and mass 2. In fact, in string theory, it is well known that the masses are in fact quantized in so that masses are square roots of integers in the alpha prime units. But the challenge is that the number of physical states for each mass level, so this n1 for each integer here, is exponentially high. So if you try to crank up the energy and produce more and more of these particles, then the degeneracy is huge. So directly, this approach is not possible. But what it tells you about is that when you look at how the amplitude behaves as a function of energy, as you increase this energy, you're going to cross these production thresholds. And every time your energy S crosses this quantity here, so square root of an integer plus a square root of an integer, all squared, then there's going to be a new discontinuity associated with these new states being produced. Okay, so we see that what we're looking for is some crazy function that has infinite number of discontinuities, and these infinite number of discontinuities have to arrange themselves into these square roots. Okay, so I believe this is essentially the reason why an analytic formula for this object isn't known, because if you had such a formula, you would have to reproduce all these complications. But nevertheless, we can already start with kind of producing a tentative plot that we would expect from a one-loop amplitude. So again, without doing any computations, what we can already predict is that if you plotted this amplitude, so here I'm going to focus just for concreteness to t being equal to minus s over 4, which corresponds to a 60-degree scattering angle. We don't know exactly how this formula looks like, but we know that it has to have a discontinuity every time S hits the production threshold. So I've actually indicated that with these dashed lines. Hopefully you can see them. So each of them corresponds to a given masses being produced in the cut. So for example, this one is square root of 3 plus square root of 5 all squared. Okay, and I should also say that one idea that you might have had is to use the alpha prime or low energy expansion of the amplitudes. But it actually turns out that the alpha prime expansion is only valid in up to the first resonance. So if you actually wanted to predict the behavior of the amplitude in the high energy, the alpha prime expansion is not terribly useful. Okay, so that was the first piece of information. Now we can hunt for other pieces of information. So the other question would be, what is the asymptotics of a large energy behavior? Okay, so the large energy behavior can in principle be studied using the saddle point approximation at fixed angle. And if you actually try to do this computation, you would find that in principle, in this variable tau, there's an infinite number of saddles that can contribute. But what this tells us is that if you evaluate the integrand on the saddle, each of them would give you some exponential suppression multiplied with some factors, the CI. So there's been actually a working hypothesis in this field that there's a single saddle that dominates the whole one-loop amplitude. So that's due to the work of Gross, Mende, and Magnus back in the late 80s. So that would tell you that there's a single saddle, and more or less, moreover, you can predict that its value would correspond to the tree-level suppression. So that prediction would be that the exponential decay is essentially the same as at tree level. There's been actually some speculations about how this resounds at higher genus, although I will not have time to explain it. Okay, so but one thing that I wanted to emphasize is, of course, the question of which saddles are relevant to a given computation depends on the integration contour that you study. And I just mentioned that we don't know what the integration contour is. So of course, we don't actually know the answer to this question. So what we'll see is that this story of the one loop amplitude being dominated by a single saddle is actually cannot be entirely correct. But then nevertheless, we can tentatively put some indicating lines. So once again, we're on a logarithmic scale. So what this means is that the exponential decay would be following some kind of straight lines that look like this. And the straight lines would have to indicate the exponential decay, which was the same as at tree level. Okay, so we're learning more and more without doing any detailed computation about this object. In fact, we know slightly more. And this relates to one of the questions that we had, which has to do with the durations of the annulus and the Mobius strip topologies, in which you shrink in which you pinch the particles 1, 2 from phi 4 in the following way. So if you actually try to make an analogy with Feynman diagrams once again, this would correspond to this kind of Feynman diagram, in which you have some 1 pi decoration of a single propagator. Okay, so this tells us two things. First of all, at every integer, so there's going to be a simple pole corresponding to this propagator here, to this propagator here. So overall, there's going to be two poles. And there's going to be some residue on these poles, and that residue is related to this 1 pi decoration. But we know what this 1 pi decoration means from our quantum field theory classes. It tells us about the mass shifts and the decay widths, and more precisely, the real part is related to the mass shifts, and the imaginary part is related to the decay widths of strings. So that's great news for us because these quantities have been computed in the past, again, by a long list of people. So we have some data that we can put now on the plot. So the data is the fact that we know the behavior close to integers. And in fact, so we get a better picture. In fact, what I'm going to do is I'm going to plot both the imaginary part and the real part in blue and orange respectively. And I'm going to multiply them by the sine pi s squared. So the sine pi s squared is only so that, once again, so that the plot is more readable. I'm just going to put a double zero in the place where there's a double pole so that the curve is going to be smooth. And all these data points that you can collect from the literature correspond to some kind of behavior that roughly seems to be following this exponential decay. Okay, so so we get the data point for every integer. And there's a crucial thing that I wanted to emphasize here. So remember that this plot is actually plotted on the logarithmic scale. So if you look at the difference between the imaginary and real part, the imaginary part seems to be vastly leading over the real one. In fact, it leads by a couple of orders of magnitude. So the imaginary part is leading. So you see something that you might have thought was a pure subtlety, some I epsilons, blah, blah, blah. It actually turns out to be the leading effect in the final answer. Okay, so you absolutely cannot forget about this issue about Feynman I epsilon description in string theory. Okay, so this is pretty much as much as we can get without doing an explicit computation. So what I wanted to explain to you next is how to kind of come back and revisit this integration contour. So the integration contour, yes, please.
No, I just missed that. I just missed the part where you explained why the imaginary part of the amplitude is much greater than the real part. I missed what the reason was.
Yeah, so you have not missed anything. I've not actually given you the reason. This was just the output of previous computations.
Okay.
Yeah, it turns out it can be actually explained, although I will not do it in this talk. It can be explained by studying crossing properties of planar amplitudes. We can talk about it more after the talk. But,
Sure.
Okay, excellent. So
actually, sorry, Sebastian. I don't know, maybe just some.
Yeah,
it's not really a problem. There is actually one blue point which is below the orange point, right?
Yeah.
Is just some
Yeah, it's not clear. From this data, it's not clear, but we're going to explain it in about 5 slides.
Okay, I see. Okay.
Okay, excellent. So now we have to come back to the contour. And remember that the original contour was the one that was integrating over all geometries, all thicknesses of the annulus. So at the bottom end, it corresponded to a thin annulus. So basically a Feynman diagram. This is the limit in which you need the I epsilon prescription. And there's also the opposite end of the spectrum, which corresponds to the thick annulus, which you can think of the internal boundary of the annulus as shrinking to a point. So it looks kind of like a point insertion, but at 0 momentum, and it's actually associated to a divergence. Okay, so first of all, let's address the I epsilon issue. So it turns out that the way that you can implement it is by modifying the contour to look like this, so close to 0. It turns out that for consistency with quantum field theory causality, so matching on the Feynman I epsilon, the limit as the Feynman diagram limit, it requires you that the contour actually looks like this. So the key point about this is that there's actually an essential singularity at the origin. So the direction of the approach of the singularity is going to make a difference. In fact, the direction of the approach from the upper half plane directly down is going to be divergent, but the one that is plotted here is going to be finite, and the one that I'm claiming is also agreeing with the causal I epsilon prescription. Okay. So in fact, you can repeat this analysis also for the Mobius strip, and the story is entirely analogous. There's also the same contour, but now shifted by a 1/2. Also, there was, if you remember from the previous slides, there was a minus sign and a factor of 32 over n. And as I mentioned before, in the limit as the I epsilon, in the limit as tau goes to I infinity into the upper half plane, each individual contributions of both planar annulus and the Mobius strip are actually divergent. But their divergences can cancel out, and in fact, cancels out only if n, so this was the n from the gauge group, is equal to 32. So you see that only the SO32 out of SONs is allowed, that cancels the divergence, which is a well-known fact. Okay, so before computing, so basically the challenge is going to be now to evaluate this integral over this contour, but before doing the full computation, what I'm going to do is I'm going to explain how to just compute the imaginary part. So the imaginary part is simple because it's the difference between the I epsilon, which is the deformation with the right hooks, and the minus I epsilon, which is the deformation, which would be the deformation with the hooks to the left. The difference between hooks to the right and hooks to the left are just these circles. Okay, so these circles compute the imaginary part of the amplitude. And in fact, the amplitude, there's a lot of danger on the real axis because of the essential singularities, but in the upper half plane, the function is entirely holomorphic, which tells you that I can actually shrink them to be arbitrarily small, but non-zero. So I can exploit this fact to actually just Taylor expand everything around tau equals 0.5, and this will give me the answer. Okay, so if you actually go through the motions and implement that procedure, it tells you about the imaginary part of the amplitude, just superimposed on the previous plot. Okay, so this nicely matches on passes through the integer points that we knew about before. So these are these dots. And actually, this refers to the question that we've had. It also passes through these points here. And this is related to the fact that there are zeros in the imaginary part. So they look like spikes just because we're on the log scale, but they're really zeros of the imaginary part. Okay, and we see that on average, they follow the exponential decay predicted by Gross and Mende. And on top of that, it turns out that this formula actually has, or this curve has a lot of discontinuities. In fact, it has a discontinuity at every dashed line, but they're barely visible because they open up very slowly, although we can prove that they're there. you would not directly see it from the data. Okay, so this concluded the computation of the imaginary part. Now what we wanted to do is complete this computation and also compute the real part. So if you wanted to compute the real part, you actually have to evaluate the full contour, the one that we've seen on the couple of slides ago, which looked like this. And one aspect of it that I already mentioned is that everything is holomorphic in the upper half plane. So that means that these contours, you can actually wiggle them around, you can deform them, as long as you don't change the fact that they approach 0 and 1/2 with the correct angles. And we can, in fact, use this to split this contribution into the kind of parts that you can deform all the way to infinity, and the one that you can, which is lowercase gamma, and the one that you can deform to the 0, which is capital gamma. It turns out that the upper one is actually related to the renormalization of alpha prime, which is something that I wanted to explain more about if I have time left over. But for the current part, I'm going to just tell you about the most difficult part of this computation, which is computing this integral here. And here it would actually help if someone could tell me how much time I have left.
10 minutes.
Okay, so if we have 10 minutes, I'm actually going to fast forward through the technical part of this computation. Let me just kind of flash the outcome of this computation. The outcome is that you can actually deform this contour into the crazy fractal contour that looks like this. Okay, so this at the looks like a complete nightmare. It on the face of it. But the reason why we do it this way is that each of these circles is almost exactly the same computation that we've already done for the imaginary part. So basically, each of these circles, we have some power series in these circles, and all of them can be once again shrunk to a point, and then you can compute those. So if someone is interested, I would love to go through the details of this computation in detail. But the bottom line is that it converted what essentially was a complicated integral into an infinite sum representation. So roughly speaking, now we have to do a sum over these circles, and from this picture, the biggest ones are the ones that contribute the most. So that tells you if I truncate the sum at some finite with some finite cutoff, it means that I would be actually able to approximate the integral to arbitrary accuracy. So this is what we've done. And the outcome.
Excuse me. What is
Yes?
the final result for the asymptotics behavior? What is your answer?
Yes. So you're asking about the convergence of the series?
No, not about conversion. About high energy asymptotics.
Yes. Okay. Excellent. So this
For
leads us to,
tachyons, I believe, right? You consider tachyons.
no, it's for gluons. It's for external gluons.
No, okay. What is the answer?
So the answer is actually contained in this plot. So what we've added on this plot here is the real part, which is plotted here in orange. Okay, so let me explain. This is the main plot of this talk. Let me explain the couple of its features. So it's once again, it's difficult to compare with the previous result in the alpha prime expansion because all of them are contained kind of in one pixel in here. They break down at the first resonances. Let me emphasize that this is actually would be a very difficult computation if you did it in a kind of say string field theory or string or field theory perspective, because what you have to do at these high energies. I mentioned that the degeneracy of the states is very high. So if you actually try to count how many two-particle states you would have to sum over, these are the all different excitation modes of string theory, there would be roughly 10 to the 50. Okay, and then once again, let me emphasize this feature that everything is dominated by the on-shell particle production, which is to say that the imaginary part is much bigger by a couple of orders of magnitude than the real part. And then finally, we also see wiggles that would be, I mean, it would be, I believe that would be quite difficult to establish their presence analytically, but nevertheless, we can see them numerically. And they're roughly due to some very complicated, possibly chaotic string dynamics of the different excitation modes that are being excited in the scattering of the two strings. So to address the question about the high energy behavior, we see that roughly speaking, they follow these dashed lines, which was the Gross-Mendel behavior. But the Gross-Mendel behavior cannot be entirely correct because of the additional oscillations that do not die out at infinity. So that most likely indicates that there's not one, but at least two or more saddles that actually contribute, possibly with the same real part, but different phase. Okay.
So it's correct to say that it's not clear what is asymptotic. Is it what you say?
Yeah, so asymptotics on average follows the exponential decay with the tree-level action, but on top of that, there's some oscillations that are not understood analytically yet.
Okay, thank you.
Thank
It's complicated.
Yeah, it was very complicated. Okay, so in the last 5 minutes, let me also explain the other aspects that are very interesting. So far we talked about the fixed angle scattering, and I flashed this plot. Let me also mention the fixed momentum transfer scattering, which is another way of taking the high energy limit, which is related to the so-called Reggie limit. Okay, so here let me just cut to the chase using exactly the same technology, same contours and infinite sum expansion. You can actually compute the amplitude. So this is the same quantity, the planar contribution at as a function of s at the fixed momentum transfer, which I took to be 0. Okay, so it's a forward limit. And then in the forward limit, you see that the real part here in orange oscillates around 0, but the imaginary part is going roughly to a constant. And in fact, here I even rescaled it by a factor of 20 so that they fit on the same scale. So imaginary part once again dominates. So this is a result from last year. Let me also share a preliminary result that we're working on in the closed string. So it turns out that all of that story with the I epsilons and the complicated contours can be repeated for the closed string scattering, which is more complicated but can be done. And we have some preliminary results on the behavior of the amplitudes for the real and imaginary parts. But for now, let me bring your attention to the fact that the imaginary part in the forward limit goes mostly as a constant. Okay, so this actually leads to a small puzzle that was there for some time.
May I ask a question? The imaginary part of the closed string amplitude, this is in the Regge regime for S large. This is the three-level amplitude.
This is the one that
looks, yeah, but should goes like a square.
Oh yeah, excellent. Yes. So
how do you get?
Yeah, exactly. Yeah, that's very good. So actually, you could have had this complaint already here. So maybe it's not entirely transparent because I stripped away this T8, the normalization up front. But to make it, basically there's a tension between these one-loop results and the expectation from Reggie behavior. So I will try to explain this tension now. So I think this is better illustrated on the fact that the imaginary part is related to the total cross-section. So let me explain it. The total cross-section, which is related to the to the amplitude by taking the major part and multiplying the fourth limit and then multiplying by a single power of s. So what these results indicate, which is the black line, is that the cross section grows roughly linearly with a single power of s, which is in contradiction with what you would have expected using, say, Regge behavior. Regge behavior would have told you that the amplitude actually has to saturate. So it would tell you that it goes as s to the the cross section would have to go to a constant. So it grows too fast.
Is this for open string in the open string case? No, this is for gluons.
Yes, that's right. Let me maybe explain a little bit that these different colors here, they refer to the partial cross sections that I've split into the contributions of different masses of the particles being produced. So you can see that there's different thresholds that open up. So these opening ups are the new particles being produced, and they open up very slowly, as indicated on the previous slides. Okay, so the little puzzle is that this grows linearly, while you would have expected that the cross section goes to a constant. So let me explain first of all, where this comes from and how to resolve this puzzle. So the bottom line is going to be that this is kind of a mirage that you see at one loop level. You would actually see it at every order in perturbation theory, but that statement is going to resum, and it's going to resum into the correct Regge behavior. Okay, so first observation is that everything is dominated by this cusp contribution, the thing that I mostly ignored, except for the fact that I told you that the one loop with the inner boundary shrunk to a point, you can think of it as an alpha prime derivative of the Veneziano amplitude. So if you actually plugged it in, just to convince you of that fact, if you computed the alpha prime derivative of the Veneziano amplitude, you would find that it gives you this answer. So in the forward limit, when t goes to 0, it would go as a constant. So that means the cross section would grow linearly. So it's certainly a true fact. However, you can, having recognized this pattern, you can actually continue it at higher genus. So at higher genus, here I've illustrated this at genus 2. You have multiple surfaces, and you can think of it that for every handle, you can either connect it straight or you can twist it. Okay, so here we've twisted, and twisted twice. And likewise, you can study this limit in which all the inner boundaries shrink to a point. And in that limit, it turns out that once again, you can think of it as the insertion of two soft zero momentum particles. And this time they're related not to the first derivative of the alpha prime, but to a second derivative. So we have a second derivative hitting the Veneziano amplitude. So it turns out this pattern actually continues to higher genus. So if you study the planar amplitude, or the contribution to the planar amplitude from these cusp contributions, that at any given genus G, it's going to have a G derivative of alpha prime, and I've actually included all the numerical factors. Okay, so as you can recognize, G, there's a 1 over G factorial, and there's G's in the powers. So this actually resums. It resums in this limit into an exponential. So now what we have is that we have an exponential of a derivative hitting an object. And of course, you can think of that exponential of a derivative as a translation. Okay, so the effect of all these computations is the fact that the alpha prime is supposed to be translated into adding a small phase. Okay, so we add a small phase e to the I g string squared over some numerical factor of 4 pi squared. So what this means is that if you actually perform this resummation, so just take the net result is that you take the Veneziano amplitude and you make this substitution. In fact, G string is small, so you can expand it, and it gives you this resummation. And that resummation now decays as 1 over s. So that means that the cross section grows as s to the 0, which is the correct saturation to a constant. So precisely as expected from the Reggie behavior. And let me give you an alternative interpretation of this result. So the interpretation was that the way that we should think of this resummation is as renormalization of the alpha prime. So one aspect of it is that I mentioned before that the spectrum, normally you would think of the spectrum of the strings as the masses squared being equal to integers in the units of alpha prime. But now alpha prime is renormalized. So one thing that happens is that the masses actually get a correction. So masses get a correction with an imaginary part here. So what this means is that while previously there was a question about resonances, at tree level you would hit resonances at 0, 1, 2, 3, and so on and so on. The effect of this resummation is that essentially all these resonances move to the lower half plane, and they now look like they have a width, which is very much consistent with our previous explorations into widths at one loop. Okay, so this is the renormalized spectrum of this order in perturbation theory. So if you study the physics on the real axis, this is the one that gives you the resummed correct Reggie behavior. In fact, this squares really well with something that people have been doing for a while already, which is an alternative prescription. If you just shift all the poles back to the real axis. So if you imagine, if you didn't know about this resummation, one thing that you could have done is you could have studied the physics slightly into the upper half plane. So studied it at some angle that looks like this, and you would have obtained the same result. Okay, so these are two kind of equivalent pictures. Okay, so I believe I'm well out of time. So let me just tell you that this is just the tip of the iceberg. We nowadays understand more and more about string perturbation theory from these explicit numerical computations. And then we can study, say, partial waves. You can study cuts using different topologies, different planar orderings, different types of strings, and so on and so on. So you can find some references in here. And for the purpose of this talk, let me just summarize, go through the outline and summarize what we've learned. So I started this talk by motivating it by studying the phase diagram of gravitational scattering. And I explained this interesting question about the behavior of string theory at high energy, which in principle is going to teach us more things about the transition between string and black hole dynamics. And then we decided to have a concrete handle on these kind of questions in string perturbation theory. And I told you a little bit that if you actually wanted to extract numbers out of the worldsheet integrals, you have to actually face some challenges that have to do with the choice of the integration contour and how to actually compute it. And then what we've done ultimately is we resolved those puzzles, and that led to the first computation of the one-loop scattering amplitude in string theory at finite energy. And it gave us this plot from which, with a lot of wiggles and the exponential suppression, from which we've gathered a lot of information. And I also explained to you how we can talk about the cross-section, and in particular about the all-genus resummation of the contributions to the cross-section. Okay, so with that, I would like to thank you for your attention.
Can I ask you a question?
Irina, you are muted.
I'm sorry. Oh, please, questions. I was unmuted. Sorry. Questions, please.
Can I ask?
Yes, please.
Please, can you compare your work with Amati Cefaloni-Veneziano work?
Yeah, so of course the work of Amati Cefaloni-Veneziano is enormous. There's many different aspects that we can try to compare. I think myself, so there's perfect agreement between the two approaches. Perhaps one of the points of contact was this kind of resolution of the puzzle in which there's a difference between perturbative computations at the given order in the genus loop expansion and the resummation. And that's actually perfectly consistent with the predictions of Amati, Cefaloni, and Veneziano, who studied the Regi asymptotics, for example, of string amplitudes.
Okay, thank you. I have another question. In quantum field theory, the normalization group method is very useful. What about this method in string theory? Are there
Yes.
some more
Yeah, that's a good question. The way that well, so the only parameters that you have are the G string. You can also think of the alpha prime as a parameter, as I mentioned here. So yeah, you can think of this aspect that I mentioned here, this kind of resummation as a well, essentially it came from what in string theory, what in quantum field theory would be the analog of the one particle irreducible resummation. So it's kind of a similar feature to what you would expect from, say, studying how the pole mass of a particle shifts under adding the counter terms to the propagators. There's a kind of analogy there.
Okay, thank you.
Thank you.
Okay, I see the questions from Deepak. Please ask your question.
Yeah. Thanks for the talks, Sebastian. So okay, so you'll forgive me if I'm, if my question is not as concrete as one might wish for. So when you say that you're talking about, let's say, the large energy limit of string scattering, right? You're taking the center of mass energy to be large.
Yeah.
So basically, you're ignoring the extended the fact that the string is an extended object. I mean, it doesn't just become a point particle in that limit, and where do the extended body dynamics of strings hide in this?
Yeah, sorry. Yeah, that's a good question. So we're certainly not ignore. So it's true that at high energy, the individual string looks more and more like a point particle. So that's certainly true. So you would imagine that if you go on to a high center of mass energy, then we can approximate everything as a point particle. However, there's a subtlety with that, and the subtlety is that really the string has multiple excitation modes. So every time we increase energy, you can actually excite the string more and more. So these are precisely the effects these are the what I call the high mass level strings or highly excited strings. And they definitely contribute to the high energy behavior. And in fact, they cause all these wiggles in here. So all these dynamics of how these modes interact is important at high energy.
Okay, so I mean, just to clarify, so basically, at high energies, you can think of the string as a point particle with lots of internal states.
Yeah. There's the oscillator modes of the string. Exactly.
Right.
Yeah.
Right. Okay. This the second question. I mean, if I may ask, unless Philip is waiting.
Yeah.
Okay. So ultimately, one would like to connect this to something that one might observe, right? So, for instance, one might expect that beyond certain energy, let's say the 4-gluon scattering amplitude you calculate from QCD would have to be corrected by something from string theory. So, does this help us, reach any closer to possible observational predictions?
So let me, that's a great question. So let me clarify a couple of points. So first of all, my motivation for studying this is, of course, purely theoretical. But if we wanted to make connections with potential future experiments. Let me clarify that the first resonance that you would see would be here. So this would be the S equals to 1 in the units of alpha prime. So that's a tunable parameter. So presumably the physics that we would see now is the one below that resonance, because we have not reached yet enough energies that could probe it. So in that regime, in which you're below the first resonance, you can actually expand the amplitudes in the low energy expansion. So that's actually perfect. The regime in which we have a very good control over perturbative computations in string theory. This is the alpha prime goes to 0 expansion that I mentioned here. And essentially, you can think of it as effective field theory contributions, corrections to, say, gluon amplitudes. So basically, you can classify the higher derivative operators that are a consequence of the low energy behavior of strings, and that's something that
S is equal to 1 is already much larger than, let's say, the LHC energy scale. Is that like?
Yeah, that's right. That's right.
Is it already larger than the string scale?
Yeah. So again, string scale is a tunable parameter.
Right.
But by the fact that we have not observed any string resonances in the wild, it means that we are somewhere here on the plot. So in a sense, all of this wildness is way when you're sensitive to multiple resonances. Certainly not something that we would be able to access.
Right. Okay. Okay. Thanks.
Okay, I see one more question.
Excuse me. Actually, I have one more, if it's possible. You mentioned the I epsilon problem.
Yes.
What do you think if we just use an Euclidean formulation? Is it all right?
So in the Euclidean form, yeah, that's a great question. So in the Euclidean, let me kind of explain where the problem came from. The problem came from in the formula, from the fact that there's in this formula here, there's a minus s and minus t. So there's actually an essential singularity when this factor goes to 0. So the problem is when s is positive and t is negative, or s is positive is the relevant quantity. So you can study this in the Euclidean. If by Euclidean we mean Euclidean scattering, so like scattering in unphysical signature.
Yes,
then s would be negative, t would be negative, and in that regime, you can actually compute the first the planar annulus. You can actually compute without any I epsilons. That's as expected, because basically what happens is that the all complications are because of the resonances that they cross. But if you work in the unphysical kinematics as negative, t negative, then you're below all the thresholds. So if you're all below all the thresholds, there's no imaginary part, there's no subtleties with the I epsilon.
Okay, the next question from Philippe. Philippe, please ask your question.
Okay, I just wanted to very quickly comment on the point-like limit at very large S. I think where you'll still see the extended structure is in the rate at which you approach infinity. Not the actual value at infinity, but the gradient as you're coming into infinity. That's the comment. And then the question is, the way you've unitarized by summing over all genus is very interesting, and you get a very nice result. But it seems that every particle in the system becomes unstable unless they're massless. So what does the lightest unstable particle decay into?
Yeah, so first of all, that's a correct assessment. All the particles become unstable. And the way the channels that you can study the channels in which they decay. So of course the first mass level can decay into 2 massless. So everything is decaying into lighter excitation modes. But it's actually absolutely true that the excited modes they start decaying, so producing other particles, other string states, and so on.
Okay.
The only one that is stable is the massless, in this case.
Massless one is stable, yes.
May I ask a question?
Yes, please.
About the mass shift, the mass corrections, probably one of the last slides.
Mhm.
Essentially, you found a constant correction. So the shift you found does not depend essentially on the state, which is
Yep.
decaying.
Yep.
How is it possible? Do you have some explanation? Because
Yes.
I can compute the same mass shift, so the G string square correction.
Yes.
Computing the mod square of 3 level amplitudes,
Yep.
so summing over mod square. And then we know that the emission of a string will depend on the initial state. So how do you get this shift, which is the same shift for every state?
That's an excellent question. There's actually two parts of the answer. Maybe the simplest aspect is that this is only the asymptotic statement. So this is the correction to the imaginary part of the mass squared as s goes to infinity. So the statement is that all
But
these
the number, the mass shift doesn't know about the s goes to infinity. Mass shift is a number. It's,
yeah, exactly. So what this says is that this formula is exact in the limit as the n goes to infinity. So for very, very excited states, and then you can try to compute corrections to it. In fact, these are the things that can be computed, as you're saying, and they were mentioned here. Sorry for back and forth. These are the dots here, right? So this is what you're talking about here. That the imaginary part. So these dots here indicate the mass level 1, mass level 2, 3, 4, and so on. If you computed it case by case, so you can see that on average they actually follow. They coalesce. And that's more or less the statement that I'm trying to make. That in the limit, as the mass level goes to infinity, they become more and more uniform. But I actually wanted to also mention, this was the first point. I also wanted to mention the other caveat. The other caveat is that when I'm talking about mass shifts, this is really an average mass shift, an average decay wave. And the reason for that is that when I do a cut, so when I look at the residue of this, I'm essentially putting these particles on shell.
Mhm.
But I mentioned that the degeneracy of the states at the fixed mass level is exponentially high. So when we extract these mass shifts, it's really an average over all these exponentially many different levels.
I see. This is not the mass shift for fixed degeneracy.
Yeah, exactly. Not for a fixed state. It's instead summing or averaging over all states.
Averaging over all the. I see. Okay, I understand now. Thanks.
Of course, if one wanted to do a more detailed analysis, this can be done case by case, at least for the light excitation modes, and that's actually contained in large parts in these papers in here.
Yeah, there are. Okay, thanks.
Yeah, thank you. Excellent question.
Okay, more questions, please. I don't see people who want to ask more. If not, let's thank the speaker for a very interesting talk and for interesting discussion. Thank you very much.
Thank you, Sebastian.
Thank you.
Thank you, Sebastian.
And actually, if you can send us the slide,
Thank
we can
you.
upload them on the website if it's
Yes.
okay for you. Okay.
Absolutely.
And thank you very much.
Thank you.
Thank you.
Thank you.
Everybody.
Thank you. Bye.
Thank you.
Have a nice day.